Hello everyone. Once again welcome to our physics class. Hope you all are fine over there. In the last session we had discussed about the force experienced by a current carrying conductor in a magnetic field. Also we discussed the Fleming's left hand rule. So in all these cases we have found that electricity leads to magnetism. Is the reverse process possible? Can magnetism leads to electricity? What do you think? Yes, it's possible, my dear children, and it was discovered by a brilliant scientist, Michael Faraday. And the concept is known as electromagnetic induction. So today, let's talk about the experiments with which. So today, let's discuss about the experiments which led Faraday to the concept of electromagnetic induction. Let's get started with today's session. Children, Michael Faraday proved this electromagnetic induction through his 3 experiments. So we are going to discuss his 3 experiments which led him to the concept of electromagnetic induction. On the screen you can see a coil, and this circular coil is connected to a galvanometer. You know the function of galvanometer. Galvanometer is used in any circuit to detect the presence of current flowing through that circuit. So if current flows through this coil, galvanometer needle will deflect. Okay. Now here you can see a magnet. This is the north pole of magnet and this is the south pole of the magnet. Now this magnet moves into the coil. That means this is a moving magnet. And this magnet is approaching towards the coil with north pole pointing towards the coil. Okay, so the north pole of the magnet points towards the coil and it is approaching the coil. So when the magnet moves into the coil, just look at the needle of the galvanometer. What happens to galvanometer needle? It deflects to right. Okay. Now, just look at the second figure. Here, the magnet has reached inside the coil. Now, the magnet is at rest. It is not moving. It is stationary. Just look at the galvanometer needle. Yeah, it does not show any deflection. Okay. Now, just look at the third figure. Here you can see the magnet moves out of the coil. That means he moves the magnet backwards. Just look at the galvanometer needle here. What happens to galvanometer needle? It again deflects, but this time the deflection is towards left. So just compare these 2 figures. Here, when the magnet was moving into the coil, the galvanometer needle deflects towards right. But at the same time, when the magnet moves out of the coil, that means in the backward direction, the galvanometer needle deflects in the opposite direction towards the left. Now here just look at the final figure or last figure. Here you can see the magnet is kept at rest and the coil moves towards the magnet. This time also the galvanometer needle deflects towards right. Okay, so here the magnet is kept at rest, only the coil is moving, the galvanometer needle deflects towards right. So in all these experiments, one thing is very clear: the galvanometer deflects only when the magnet is moving. When the magnet is at rest, the galvanometer needle does not show any deflection. Just look at this figure. In the first figure, the galvanometer deflects because the magnet is moving towards the coil. But in the second figure, the galvanometer needle shows no deflection because the magnet was at rest. And the third figure, again the galvanometer needle shows some deflection because the coil was moving in the backward direction. And here also, but here the magnet is at rest At the same time, the coil was moving. So one thing is clear, the relative motion between the coil and magnet is very essential for the galvanometer to deflect. Okay. Now, when galvanometer deflects, what does it mean? Yeah, it means that a current is flowing through the coil, because galvanometer detects the presence of current. Whenever current flows through the coil, it deflects. So here the galvanometer deflection indicates the presence of current through the coil. Here we have not connected any battery. Any battery source is not here. So how does this current flow through the coil? Again, the current flows through the coil only when there is a relative motion between the coil and the magnet. So what could be the reason for this current? Can you guess? Children, let me explain. Here, whenever the magnet is approaching towards the coil, what happens? Here you can see some lines. Can you? See, these lines represent the magnetic lines of force. You know, around the magnet we can depict magnetic lines of force. So these lines are the magnetic lines of force for this magnet. And when the magnet approaches the coil, or when it moves towards the coil, the number of magnetic lines of force linked with this coil increases, right? Okay, so what happens whenever the magnetic lines of force linked with the coil increases, the magnetic field also increases, right? So there is a change in the magnetic field associated with the coil. The magnetic field increases, or the magnetic lines of force increases. So due to this change in magnetic field, a current is induced in this coil. Now in this figure, the galvanometer needle does not show any deflection. What could be the reason? If there is no deflection, there is no current through the coil. Why? Here the magnet is at rest, right? So the lines of force associated with this coil is not changing. If 10 lines of force is associated with this coil, since the magnet is at rest, 10 lines of force will be associated with this coil always. It's not going to change. So there is no change in the magnetic field associated with this coil. So whenever there is no change in the magnetic field, no current is induced in the coil. Hence, galvanometer does not show any deflection. Now, look at this figure. Here, the magnet is moving backwards. So what happens to these lines of force? Yeah, these lines of force associated with the coil decreases, because the magnet is moving away from the coil. So the lines of force associated with the coil decreases. That means there is a change in the magnetic field linked with this coil. The magnetic field associated with the coil also decreases. And due to that change, a current is induced in this coil, and that current is indicated by this galvanometer. And this time the direction of current is towards left. This time the current is flowing in the opposite direction as that of this case. Okay, that's why the galvanometer shows opposite deflection in this case. Now look at this last figure. Here the magnet is kept at rest. So still there will be lines of force associated with the coil, because the magnet is close to the coil. Now when the coil moves towards the magnet, what happens? The coil is approaching the magnet. So the lines of force associated with this coil increases, right? Because the coil is moving towards the magnet. So the number of lines of force associated with this coil increases. That means the magnetic field linked with this coil increases. There is a change in the magnetic field. It has been increased. So whenever there is a change in magnetic field, a current is induced in the coil, and that current is indicated by this galvanometer deflection. That's why the galvanometer needle deflects towards right. Okay, so from this experiment, it is very clear a current is induced in the coil whenever there is a change in magnetic field associated with the coil. So this phenomenon is known as electromagnetic induction. Here, the change in magnetic field is responsible for electric current. So electricity is induced due to the change in magnetic field. That is, magnetism leads to electricity, or magnetism gives rise to electricity. Okay, so this concept is electromagnetic induction. Now, two more experiments are there which again led Faraday to the concept of this electromagnetic induction. Now, let's move on to the second experiment performed by Michael Faraday. Here, on the figure, there is a coil, and that coil is connected to galvanometer. Let this coil be coil 1. Now we have one more coil. We can name it as coil 2. And this coil is connected to a battery. Okay. Now switch on the circuit here. Just switch on the circuit. When the circuit is switched on, current starts to flow from the positive terminal to the negative terminal of the cell. So now current flows through the coil 2. Coil is a conductor. Whenever current flows through the conductor, it behaves like a magnet, as said by our Christian Ersted. So now, since current flows through the coil 2, our coil 2 is a magnet. It has some magnetic properties. Okay, so if it is a magnet, there will be magnetic field around this coil, and that magnetic field is indicated by lines of force like this, right? Now, just move this current carrying coil, that means coil 2, towards coil 1. What do you think? Can coil 2 induce a current in coil 1? Yes. Why? Even though this is simply a coil, when it carries current, coil 2 acts like a magnet. Now, when this coil 2 approaches towards coil 1, the magnetic lines of force of the coil 2 get linked with coil 1. Right? If coil 2 is little bit closer towards coil 1, what happens? These lines of force will enter into the coil 1. So our coil 1 now gets linked with the magnetic lines of force produced by the coil 2. So what happens? The magnetic lines of force associated with the coil 1 increases. That means the magnetic field associated with the coil 1 increases. There is a change in the magnetic field. Since there is a change in magnetic field, a current is induced in the coil. As a result, the galvanometer needle deflects towards right, like this. Okay, just move coil 2 in the opposite direction. That means backwards, like this. What happens? Yes, when the coil 2, which is a magnet, moves backwards, the lines of force associated with the coil 1 decreases because coil 2 is moving away from coil 1. That means the magnetic field associated with the coil 1 decreases, there is a change in the magnetic field. The magnetic field has been decreased. Whenever there is a change in magnetic field, a current is induced in the coil 1. And this current is indicated by the galvanometer deflection. This time the galvanometer needle deflects towards left. Whenever there is a change in magnetic field, there a current is induced in the coil.